Hello everyone, this is the sixth video of 1.2 atomic structure. It's going to be the last one. Okay, in this video we'll be looking at the same thing, arrangement of electrons in atoms and monoatomic ions. We'll be focusing on ions as well as exceptions that requires you to use subshell notation. The slide that we are looking at from this point is slide 21 onwards, so last 4 slides. Okay. Now we're going to be looking at D block, which is where all the transition metals live. So yeah, middle section, which is a bit lower down compared to the rest. We'll be looking at up to zinc today, but you will be able to fill up electrons up to elements 38. By knowing all these. There are a few exceptions in that group, so we're going to look at that first. Alright, chromium is the first one and copper is the next one. I'll show you what I've done so far. So what I've done so far for chromium, 24 electrons. I have already completed the first few subshells. So 1s2, 2s2, 2p6, 3s2, 3p6. So that's the same for any element around there. So I've just done it already. What follows after? It's going to be after 3p6, 4s. Now, if there are 24 electrons, 4s2 is probably what you're thinking of putting, and the rest, 3d4 is what you'd put if you are just following what you've been taught, which is not bad, but that would be considered as wrong. So yeah, make sure you put a cross next to that line, and I'll write the right answer there. Now for S and 3D, you'd have to use them. They're the subshells, but the number of electrons are a bit different. You notice that 3D4 was what used to be the number, and there were 2. So there was one complete subshell and one not so complete, even halfway. Chromium just thinks that, hey, if there was 1 electron in 4s and there was extra one in 3D subshell, those subshells will be both half full, which is going to be a bit more balanced and more makes the whole element stable. So chromium prefers to have 1 extra electron in there instead of completing 4s. This is going to be the exception, but it's the right answer here. Okay, so that's the reason as well. It wants to be stable by having 2 half subshells. Copper is going to be fairly similar. Okay, so I've done up to 3p6 again. 4s, well, let's do it in a normal way. So you would have 2, and then 3d9, because that's the 9th element in the D block. All right, now your guess would be correct. That would be incorrect, because that's an exception and it wants to do very similar thing to what the chromium does. So copper wants to do, oops, that's a black. Copper wants to also put one of the 4s electrons into 3D. What it does is it completes the 3D shell, make 9 to 10, and 4s is going to be just half. Hopefully you can see. If not, never mind. I'll just use another color. 1. So 4s1, 3d, 10. That would be the right way of writing. Again, it's because having complete 3D shell is a lot more stable for the element. That's why it just does that. This also allows copper to lose 1 electron to be Cu1+, or allows copper to lose 2 electrons and make it copper 2+, which is more common. But both are available, and you can see that from this electron configuration. Chromium, on the other hand, it can be, just checking, it can become 3 plus, 6 plus, or 2 plus apparently. So 3 plus, I guess it has to lose 1, 2, and 3 electrons from it, and leaving 3 electrons in 3D, which is fine. 6 electrons, sorry, when it wants to be 6 plus, what it does is losing 1 and 5, or 2 to 4, 2 and 4. All the electrons in 4s and 3D can be lost, and it can bring it back to 3p6, which is possible. Also, it can be 2 plus. Well, as you can see, 2 can be available, although it prefers to have only 1 in there. But you can lose 2 electrons and keep the 3D shell as 4. So, by looking at these numbers, you can predict what ion it will form as well. Okay. Next slide. All right. I'd like to draw your attention to this diagram here. This way. So you've got energy level from bottom to up, showing energy level goes up. So the main shell 1, 2, 3, 4. As the number goes up, the energy level go up. One thing you want to notice there is that there's a crossover between the 4s and 3D. Now, this is the reason why you have to fill up 4s shell first before 3D, as it appeared on the diagonal model that I just showed you. That shows how to fill up subshells with electrons. So after 3s, 3p, you make sure you fill in 4s first, then you move on to 3d, then 4p, 4d. Okay, so make sure that 4s appears first. But another thing about 4s and 3d is that 4s shell is still part of 4th main shell. Okay, 4s shell subshell is still part of the 4th main shell. Therefore, when the electrons are taken away, as you know, electrons are taken away from the outermost shell. So 4s shells lose electrons first. Then you start taking electrons from 3D afterwards. So if you're writing electron configuration of ions of the transition metals, especially with subshell notations, what you have to do, well, firstly, you should write the electron configuration of the atom itself, then decrease the number of electrons by deleting electrons in a 4s subshell first. Then, if you manage to take both 2 electrons from 4s subshell, you get rid of 4s subshell altogether. Then you move on to 3D and start taking electrons out. Okay, so that's gonna be the order. 4s first. If the both electrons are gone, get rid of 4s, then take electrons from 3D. For example, I have put Fe, so iron, which usually have 26 electrons, but it can be 2 plus or 3 plus. Have a go at it. I'll show you an example with zinc though. So I've got zinc here, 1s2, 2s2, 2p6, and so on. At the end here, 4s should be 2 and 3d should be 10 as the end of the 3d group. Now, if you were to write 2 plus, so zinc 2 plus iron, you need to take 2 electrons off from it. Now, 4s2 is where you have to take electrons from. If you take 1, 2 electrons off, 4s doesn't have to exist anymore. So only thing that's left to do is 3d 10, and that's it. That's all I had to do. Now there are more examples that you can do, like manganese here. So have fun with this one. Manganese can form a number of ions by losing different number of electrons. So it can vary from 2 plus, 3 plus, 4 plus, 6 plus, 7 plus. Whoops. It all causes different color changes. So yeah, I might even show you how the color changes from purple to green to yellow and things like that. I'll do that in demo, but until then, can you try practicing writing electron configuration of these ions using sufficient notations? That's it. See you later.